Okay, so section 8.2 is about graphing polar equations and what they look like. And first, if you have r equals a sine theta, where a is a number, then that's a circle whose diameter is on the y-axis. So let's say a is 3, and I have r equals 3 sine theta. Then that's a circle whose diameter is on the y-axis, and the diameter is this 3. And it always starts at 0, 0. So this 3 sine theta is a circle who goes from 0, 0, the origin, all the way to 1, 2, 3 rings up on that y-axis. Whereas r equals a cosine theta is a circle where the diameter is along the x-axis, so going the opposite direction. So let's say a is the number 8. Then it's a circle because it's a cosine theta, and the diameter is along the x-axis like so, and it starts at 0, 0, and it goes 8 rings out. Yee. Okay, but these aren't the only type of equations we could ever have. A sine theta, r equals a cosine theta. There's different equations we could have. For example, we could have a graph that looks like this. What? Like a flower. What? Okay, and what we need to know about this is r equals a sine n theta. So there's an extra n in there. And r equals a cosine n theta. They're called rose curves because they look like a flower. And if n is even, so say it was 2n, then you have 2n petals. Okay, that was kind of confusing. Let's say n is 10. So let's say we have 10n. Then you have 2 times 10, 20 petals. What? If n is odd, let's say we have 3n, then you just have n petals, as in 3 petals. And a is still represented by the rings. You know, like when we had this r equals 8 cosine theta, we counted 8 rings out. Same thing here. Okay, so let's say you have this sucker and you're asked to find the equation. It's r equals for sure, and then we have to figure out whether it's sine or cosine. Well, this one's a little bit different. Cosine in theta is always on the x-axis. So it always has a petal along the x-axis. Sine does not have a petal along the x-axis. It could have a petal on the y-axis. It could not have a petal on the y-axis. That's not what determines whether it's sine or cosine. What determines whether it's sine in theta or cosine in theta is if it has a petal on the x-axis. So again, if it has a petal on the x-axis, that means it's cosine. If the petal is not on the x-axis, it's automatically sine. So since this sucker has a petal on the x-axis, it's definitely cosine. And let's count the petals. I have 1, 2, 3, I can't count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's remember, if n is odd, then you have n petals. If n is even, then you have 2 n petals. So we have 8 petals, and that's even. So to get the number that I'm going to put in the equation, n theta, I'm going to go backwards. Instead of going from n to 2n and multiplying, we're going to go from the petals and go backwards. So we're going to divide. So there's 8 petals. 8 divided by 2 is 4. So 4 is the number n. This 4 up here is going to be the number n. And again, we know it's cosine because it has a petal on the x-axis. And then the a is still the number of rings. So let's see how far this sucker goes out. How many rings? 1, 2, 3, 4, 5 rings. So a is 5. So let's put it all together. It's r equals 5, because there's 5 rings, cosine, because there's a petal on the x-axis, 4 theta, because when you have an even amount of petals, you divide by 2 to get that number in the theta. Okay, let's keep going. To figure out what your picture is going to look like for example, this rose curve is symmetric to the x-axis because I can fold it over the x-axis. It's symmetric to the y-axis because I can fold it over the y-axis. It's also symmetric to the pole or the origin, meaning I can fold it crookedly. But if you look at these circles earlier, they're not necessarily symmetrical to every axis. If we look at this pink circle, it's symmetric to the y-axis because the pink circle can fold over the y-axis. Is the pink circle symmetric to the x-axis? No, because I can't fold the pink circle down here and land on the same pink circle. Look at this orange circle. What axis is it symmetrical to? Well, I can fold it over the x-axis and it lands on itself. So it's symmetrical to the x. Can I fold this circle over the y-axis and land on another orange circle? Heck no. So it's not symmetric to the y-axis. And neither of these are symmetric to the origin because I can't fold them diagonally and land on the same thing. Okay, so that's how you look at the shapes and know what they're symmetric to. But if you're just given the equation and you want to know what's symmetric to what, there are some rules. So if you want to test if it's symmetric to the polar axis, that means the x-axis. The polar axis, then you replace theta in your equation with negative theta. And if everything pops out the same as the original, then that means it's symmetric to that polar axis. If you want to do symmetric to theta equals pi over 2, then you replace r with negative r and theta with negative theta. If you want to see if it's symmetric to the origin or that diagonal, you replace r with negative r. And after you replace all these, if your ending equation is exactly like your beginning, that means it's symmetric. Yeah, okay. And for some reason on the homework, it never says yes. It either says no or maybe. So let's keep that in mind. Okay, so let's say we have r equals 9 cosine 4 theta. First, to figure out if it's symmetric to the polar, I'm going to replace theta with negative theta. So there's my theta, and I'm going to replace it with negative theta. So 4 times, negative theta. 4 times negative theta. And when I do that, it makes r equals 9 cosine negative 4 theta. And then there's some identity that says cosine of a negative number is equal to something else. Let me figure out what it is. It's like an even odd identity. So here's that piece of paper I sent to you through your email. Even odd. Let's see. Cosine to a negative, or cosine of a negative, just spits out cosine of regular theta. So that means this cosine of negative 4 theta is just r equals 9 cosine positive 4 theta. Yee. And since this sucker end result is exactly like the beginning, that means, yes, it's symmetric to the polar axis. I can't remember if I said this or not, but